Hi guys, I appreciate y'all attending my video here. My name is Kenneth Dusman. I'm from East Central University, and we're going to be going over kind of what my thesis has been over this last year or so. So going right into it, so like the title says, we were reevaluating the Boltzmann collision terms from Harold Grad's paper and then from the 1940s, which was on the kinetic theory of rarefied gases. So basically Harold Grad used the Graham-Charlie approximation, and we wanted to go back and look at some of his findings and see if we could approximate them with the Edgeworth expansion for greater accuracy and ease. So going right into it, here's some application. Let's look at this vector field on this cow. As you can see, the red and the orange are the warmer colors here, and that means that there's a heavier flow, a faster speed, compared to what would be the blue and the green. So looking at that, we can see just, like the different flows over this cow specifically. So the Boltzmann equation, as I'm sure you know, can help us look at flow in a system, and this is just one of the applications within the Boltzmann equation that we wanted to look into at a different approximation. So here's the final form of the Boltzmann equation. We have the partial derivative of the function with respect to time, plus what would be here the velocity of the multiplied by the partial derivative of the function with respect to x, equaling 1 over the mass with our integral of the collision term here, which would be mean velocity multiplied by the final position of one particle multiplied by the position of what would be a second particle, or f'1, which would be the final position, minus the initial position of both particles. So as you can see, if we multiply by a v, or a test function, we can get the conservation equations from the Boltzmann equation, which is very good for us. So as we can see, the mass would be the partial derivative of momentum with respect to time, plus the partial gradient or derivative of momentum multiplied by the mean velocity with respect to x. Momentum follows the same rules as well as energy. As you can see in momentum, the partial gradient of density with respect multiplied by the velocity or mean flow with respect to time, and so on. We can go ahead and look at what we wanted to do with our time in this last year. Within Appendix 3, the J integrals are present. So these J integrals are a probability density function that Harold Grad introduced, and we wanted to see if we could reevaluate them with the Edgeworth expansion and find a more accurate and easier computation. So the integral of this bold x here, which being our pressure gradient exponential times e to the 1/2 x squared, negative 1/2 x squared dx equals 2 pi to the 3/2 Kronecker delta n. Kronecker delta n to the n being our pairs in our system of the particles. And as you can see, J, which was the most important that we wanted to look at, to the n, which would be nth dimensional, equals p over m integral of the Hermite polynomial, the nth dimensional Hermite polynomials. And here, Harold Grad did go ahead and switch out f with g. So we have the same look here. One thing to note is that we are, in fact, in a phase space, or a six-dimensional space. So we're looking at unitless particles here and functions. So as we got through it, we went ahead and noticed that we were going to introduce some of these tensor notations, with lambda being quite important. So as you can see, we were able to keep the pressure gradient function exponential here, multiplied by an omega dx equals lambda ij, where omega would be 1 over 2 pi to the 3/2 lambda ij to the 1/2, e multiplied by e to the negative xi xj lambda ij over 2. And that is pretty much it, guys. I appreciate y'all coming in and learning something, and have a nice day.